Okay, so let's continue with our discussion on electrochemistry. This is the second part. The last time we had a review on the concept of redox reactions. So remember that redox reactions involve two processes, reduction and oxidation, that occur simultaneously. Redox reaction is a reaction between oxidizing and reducing agent. So this can happen directly or indirectly. So when we say directly, meaning the two can be mixed together in one solution or in one container. And indirect redox reaction, the two are actually in separate containers or solutions, but they are connected electrically. So this kind of setup is actually the basis for electrochemistry. So this setup, referring to the indirect redox reaction, so this kind of setup is what we call as the electrochemical cell. So just to illustrate the direct and the indirect redox reaction, so we have here the spontaneous reaction of silver plus and copper. So if we put a piece of copper metal into a silver nitrate, so this is our solution. So if we place a copper metal into the silver nitrate solution, again, the redox reaction can easily occur. And the reaction will stop when the copper metal gets covered with silver. So that's the direct. So the other one is indirect. And remember, the redox reaction involves transfer of electrons, so there's movement. So we can use this kind of phenomenon, especially uh, since electrical energy involves movement of electrons. So if you want to use this spontaneous reaction to extract energy and do work, we need to separate the two half cell reactions by building a what we call as electrochemical cell. So this is an example of an electrochemical cell. So we'll describe in a while. So what's the setup? So basically, electrochemical cells, this is where our redox reactions can happen. So there are two types. Generally, we have what we call as the galvanic or the voltaic cells, and this is the type where spontaneous reactions occur. And then the second one is electrolytic cells. So this is where non-spontaneous reactions occur. So for both types, uh, the galvanic and then the electrolytic, these cells contain electrodes. So these electrodes, this one, so these electrodes which are immersed in the solution, this is where the redox reaction happens, meaning one electrode, the oxidation happens in one electrode, and the other, the reduction will happen in the other electrode. So usually the electrodes are just some metal strips or wires connected by an electrically conducting wire. So we call the electrode where oxidation happens or occurs as the anode. And we call the electrode where reduction occurs as a cathode. Okay, so let's explain further what happens in the assembly. Usually, our anode is represented or is represented on the left side, but this diagram is actually reversed. But usually, the anode is on the left. Okay. Um, so again, there are two kinds of electrodes. We have our anode. This is our anode. Okay. And then our anode, this is our cathode. So usually again the anode is on the left. Okay, when it's uh, when the assembly or the electrochemical cell is drawn. So our anode, again, that's where oxidation takes place, and our cathode, that's where reduction takes place. Okay, so if you notice, they are in separate solutions. So we call this separate solutions or containers as they have cell. So it's meaning this container, so one container, and then electrode, and then solution. So the half cell contains the container, and then the solution, and then the electrode. And then the same thing with the other half cell. So if you notice, also in the diagram, you have this kind of U shape, um, which connects the two solutions. So we call this actually as the salt bridge. For this particular reaction, uh, it's potassium nitrate. So the salt bridge basically is a conducting medium through which our ions can move from one half cell to the other half cell. So this is a typical electrolytic conduction. So meaning the ions, the movement of ions carrying electrical charge. In contrast to metal conduction, uh, in metal conduction, it involves electrons traveling through the wire. So another important concept in the assembly is the ion migration. So how do the ions move around, no, between the two solutions? So basically, the anions, migrate towards the anode. So in the salt bridge, so the anions migrate or move towards the anode, and then the cations, they migrate towards our cathode. Okay, and then um, we'll also describe how is the conduction of charge now takes place. So let's look at the anode on the right side. So copper 2 plus enters the anode solution. Remember, anode, that's where oxidation takes place. So the copper, from 0, it is oxidized into copper 2 plus. So the oxidized copper enters the anode solution, and that builds a positive charge, no, in the solution. So to counter this build-up, our anions from the salt bridge would enter. Okay, so again, as our copper is oxidized from copper 0 into copper 2 plus, again, the copper 2 plus enters our anode solution, uh, and that causes a positive charge buildup. And to counter this, the anions would migrate, no, from the salt bridge towards the anode solution. On the other hand, on the other side, in our cathode, in the cathode, there is reduction, right, from silver plus to silver. So what happens? Our silver plus would leave, no, the silver plus ions leave the cathode solution. Okay, so when the silver plus leaves the cathode solution, that creates a negative charge build up in here. So to counter that, the cations would exit from the salt bridge. Okay, so basically the salt bridge maintains the electrical neutrality. So if there is no salt bridge, the reaction will quickly stop. Okay, so as the result of the flow of the electrons, our electrodes will bear a charge. So our anode So this is actually for galvanic, okay, because there's a different charge of our electrodes in electrolytic cell. So our anode will have a negative charge, okay, because electrons left copper, the electrons left by copper oxidation, okay. So it's negative, and our cathode is positive, since the silver plus becomes part of the electrode. Okay, so the charge of our anode is negative, and the charge of our cathode is positive. Okay, so we have here another electrochemical cell representation. So this one we look at now, our anode is on the left. So usually our anode is on the left. Okay, the previous representation it's actually on the right. So we represent the reaction in a redox reaction by what we call as the cell notation. Okay. By the way, so take note the flow of our electron. So the flow of the electron, it's from the anode to the cathode. So flow of electron. So anode to cathode. Okay. So that's because in the anode oxidation takes place, so it involves loss of electrons. So it's the electron moves from the anode to the cathode. So in here in the anode, oxidation occurs. So from zinc 0 solid to zinc 2 plus. Okay, zinc is oxidized to zinc 2 plus at the anode. And on the right side, the cathode, the copper 2 plus is reduced to copper at the cathode. If you look at the equation, so the electron is on the left for reduction. And for oxidation, the electron is on the right because remember, oxidation, loss of electrons. Reduction, gain of electrons. So electron is written on the left. So the net reaction is zinc 2 plus copper 2 plus forming zinc 2 plus and copper solid. So what you'll do when you write the net reaction, just add the two equation. No? So the oxidation, so this is our oxidation, zinc solid forming zinc 2 plus 2 electrons, and then our reduction, we have 2 electrons plus copper 2 plus forming copper solid. So if you look at the electrons, they have the same electrons on the left and on the right, so they can be cancelled, and then you just add the remaining. So you have this net reaction. So zinc solid plus copper 2 plus forming zinc 2 plus and copper. So we represent the reaction in a spontaneous redox reaction by what we call as the cell notation. So we'll illustrate in a while the cell notation. So again, the galvanic cell, that's where spontaneous reaction happens. Okay, and in the galvanic cell, it generates what we call as the cell voltage, meaning the difference in electrical potential between the anode and the cathode. So that's called the cell voltage, or the electromotive force, or its cell potential. And again, the reaction can be represented in what we call as the cell notation. So in the cell notation, we indicate basically the two reactions, oxidation and then reduction, and then the concentrations of our ions, okay, and then the state of the reactants and the products. So for example, in this reaction, so the cell notation that's divided into two parts. We have the left and then the right. So the left is our oxidation. The right one is reduction. So if you look at its oxidation, so from zinc 0, it becomes +2. And on the right side, it's reduction from +2 to 0. So we also indicate if it's an ion that's dissolved in solution, so the concentration is indicated. So there is 1 molar concentration. And then the state is also indicated if it's a solid. Okay, so in other words, if you look at the two half cells are divided by this one, no? 2 bars. Okay, and then the substances in the reaction are divided by a single bar. So for oxidation, zinc solid to zinc 2 plus. For reduction, copper 2 plus to copper solid. So again, as a summary, so the cell notation is just a shorthand for describing a galvanic cell. So the double bar here, meaning the distinction between the two electrodes or the two processes or the two half cell. So one on the left is our anode oxidation, and on the right is our cathode. And the double bar indicates the phase boundary. The double bar represents the salt bridge, meaning the distinction, separation between the two. Okay, and then the phase boundary, because we have the solid electrode and then the dissolved ions in the solution. So meaning that's the phase boundary, solid and then the liquid, the solution. So the single bar represents the phase boundary. Okay, so basically uh, if you include, no, the 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 ions in the salt bridge. So in this case, is the potassium nitrate. But usually it's not indicated anymore. So just the double bar. Okay. So this is where we will end the part B or part 2. So see you in the next part.